Welcome to BrainOmega, PyTorch Tutorial 7. Today we're building a strong image classifier for 3 food classes, pizza, steak, and sushi, using transfer learning. We'll start with feature extraction, freezing the pre-trained backbone so we only train a lightweight classifier head, and then we'll fine-tune the top layers to squeeze out extra accuracy. You can run the notebook on CPU, but I highly recommend a GPU for much faster training. Why transfer learning? Training deep models from scratch usually demands huge datasets and lots of compute. With transfer learning, we reuse a backbone that's already learned rich visual features on a large corpus like ImageNet, and we adapt just the final layers to our small specific dataset. The result is quicker convergence, better accuracy with less data, and far less overfitting than a from-scratch model. In this project, we'll download a compact pizza, steak, sushi dataset, set up DataLoaders with the exact transforms the pre-trained model expects, and build a network that combines a frozen backbone with a custom classifier head. We'll train in 2 clear stages: first feature extraction, then fine-tuning, and evaluate the result with a confusion matrix, inspect misclassifications, and even test on a custom image so you can see how it behaves off dataset. I'll finish with a few exercises to help you go deeper, but by the end of this tutorial you'll already have a clean, reusable transfer learning workflow you can plug into your own image classification tasks. We'll start with a quick environment check so the rest of the notebook runs smoothly. First, we try to import PyTorch and Torch Vision and print their versions. This is a simple sanity check that helps you diagnose mismatches later. If the import fails, we fall back to a small helper that installs the stable PyTorch plus Torch Vision wheels, CUDA-enabled build by default, then re-imports them so you can continue without manual steps. Finally, we choose a device. If a compatible GPU is available, we'll use CUDA. Otherwise, we'll run on CPU. Keeping this logic up front makes the whole tutorial device agnostic. All tensors and models will be sent to device, and you can switch between CPU and GPU without changing the rest of the code. Let's pull in everything we'll need and lock down reproducibility. We start with standard Python and scientific tools: OS, pathlib.path, random, math, time, numpy, and matplotlib for file paths, randomness, quick math, timing, arrays, and plots. From PyTorch, we import the core torch package, NN for building models, and DataLoader to batch and stream data efficiently. From Torch Vision, we bring in datasets for ready-made image datasets, transforms, aliased as T, for preprocessing and augmentation, and to PIL-image for converting tensors back to displayable images. We'll also use TQDM to wrap loops with a progress bar so you can see training move forward in real time. A small but important piece is the setSeed function. It fixes randomness across Python, NumPy, and PyTorch, including CUDA, so you get repeatable results when you rerun the notebook or share it with others. We also set QDNN to deterministic mode and turn off benchmark. This nudges PyTorch to choose stable kernels rather than the absolute fastest ones, which keeps runs consistent. After seeding, we print the selected device so you can confirm whether you're on CPU or GPU. With imports in place and randomness under control, the rest of the tutorial will be smooth, predictable, and easy to debug. We're starting our transfer learning journey with a simple but effective dataset made up of 3 food classes: pizza, steak, and sushi. It's compact, lightweight, and already arranged in a clean image classification folder format, which means PyTorch can read it straight away without extra pre-processing. Inside the main folder called data/pizza_steak_sushi, you'll find 2 subdirectories, train and test. Each of these contains 1 folder per class: pizza, steak, and sushi, each filled with .jpg images belonging to that category. This folder structure is the exact layout that torchvision.datasets.image folder expects, so it automatically assigns labels based on folder names and builds datasets ready to load into PyTorch. If the dataset isn't already present locally, the next cell in the notebook will handle everything for you. It will download and unzip the images automatically, so you can jump right into exploring, visualizing, and transforming the data without any manual setup. Think of this as your starter pack for image classification, small enough to train quickly, but rich enough to test every stage of a real-world transfer learning pipeline, from data loading and augmentation to feature extraction and fine-tuning. Let's make sure the dataset is on disk before we do anything else. We start by creating a data/folder and defining a target path, data/pizza_steak_sushi. If that folder doesn't exist yet, we download a small zip file straight from GitHub using requests, save it to data/pizza_steak_sushi.zip, and then unzip it into the target directory with Python's built-in zip file module. After extraction, we delete the zip to keep things tidy. If the dataset is already present, we simply print a message and move on, so this cell is idempotent, safe to run multiple times. Finally, we define train dir and test dir, pointing to the train/test subfolders, and print them out. This gives us a clean, reproducible starting point. Run once to fetch the images, and from then on your notebook will just reuse the local copy without downloading again. If you're on a flaky connection and the download fails, just rerun the cell. If you want to swap in your own dataset later, keep the same folder layout so the rest of the pipeline works unchanged. Before we build our datasets, we'll grab the exact pre-processing that the pre-trained backbone expects. Modern Torch Vision models ship with a weights enum that bundles not only the checkpoint, but also the canonical transforms used during pre-training, things like resizing, center cropping, converting to tensor, and channel-wise normalization. Here we pick EfficientNet B0, a great speed accuracy balance, and load EfficientNet_B0_weights.default, calling weights.transforms, returns an auto_transforms object that mirrors the original ImageNet pre-processing pipeline. Using this is the safest way to avoid silent accuracy loss from mismatched input sizes or normalization. If you switch backbones later, ResNet, ConvNeXt, VT, just change the weights enum and regenerate transforms. The rest of your data pipeline stays the same while remaining perfectly aligned with the model's pre-training. Now that the transforms are set, we can wrap the folders into PyTorch datasets and stream them efficiently with DataLoaders. Image folder is perfect here because our directory layout already follows the convention split /class*.jpg. It automatically assigns numeric labels based on the subfolder names and applies the auto_transforms pipeline, so every image is resized, tensorized, and normalized exactly as EfficientNet B0 expects. We grab the discovered class names to confirm the mapping, pizza, steak, and sushi, and then build two data loaders. For training, we enable shuffle equals true, so each epoch sees a new ordering of images, which generally improves generalization. We keep a batch size of 32 as a balanced default and set pin memory equals true for faster host to GPU transfers when running on CUDA. Num workers is set to 0 for collab friendliness. If you're on a local machine, try bumping it to 2 to 4 to overlap data loading with GPU compute. The final line prints dataset sizes so you know how many samples you'll be training and testing on, which is helpful for sanity checks and for estimating steps per epoch. Before we start training, it's helpful to see what a real batch looks like. We grab one batch from the training loader and lay the images out in a small grid so you can quickly scan variety across classes. Because we applied the pre-trained auto-transforms, resize, tensor conversion, normalization, the tensors aren't directly display-friendly. Here we convert each tensor back to a PIL image for a quick preview. Colors may look a touch different from the originals. That's normal when you've normalized for ImageNet and then do a simple inverse for display. Each subplot shows the image alongside its class name, mapped from the integer label, which is a great sanity check that image folder picked up the folder names correctly and that labels align with visuals. If you see repeated classes or odd crops, double-check your directory structure and transforms. Otherwise, this quick peek confirms the data pipeline is wired up and ready for training. Time to build the model. We're starting with EfficientNet B0 loaded with pre-trained weights, then swapping its final classification layer so it outputs exactly 3 logits, one for pizza, one for steak, one for sushi. In EfficientNet B0, the body of the network lives in features, and the classifier head is a small sequential block at the end. We read the number of incoming features from base_model.classifier open bracket 1 close bracket dot in features, then replace the head with a simple dropout arrow, linear stack. Dropout adds a touch of regularization, and the new linear layer maps those features to our 3 classes. This gives us a model that keeps all the rich general-purpose visual features learned from ImageNet, while tailoring the final decision layer to our specific problem. For the feature extraction phase, we freeze the backbone by setting requires grad equals false on all parameters in base model.features. That means backpropagation will only update the new classifier head, not the convolutional feature extractor. The benefits are twofold. Training is much faster and less data hungry, and you get a surprisingly strong baseline without touching the heavy part of the network. We then move the model to the selected device, CPU or GPU, and print a quick trainable parameter count so you can see how small the head is compared to the full model. After we get a solid baseline, we'll switch to fine-tuning by unfreezing a few top blocks and training with a smaller learning rate. That second phase lets the model gently adapt its higher-level features to your food images and usually buys a few extra points of accuracy without overfitting. Let's set up a clean, reusable training loop that you can drop into any image project. We start with a tiny helper, accuracy from logits, which turns raw model outputs logits into class predictions by taking the argmax, then compares them to the true labels and returns the batch accuracy as a plain Python number. The core work happens in run epoch. We switch the model into train or eval mode depending on the flag. This matters for layers like dropout, batch norm, move each batch to the selected device, and run a forward pass to get logits and cross-entropy loss. When train equals true, we enable gradients, zero them efficiently with set to none equals true, backpropagate, and take an optimizer step. When train equals false, gradients are disabled for speed and memory savings. Throughout the loop, we keep running totals of loss and accuracy, weighted by batch size, so the epoch averages are correct even if the last batch is smaller. You'll see TQDM wrap the loader to give a smooth progress bar without cluttering your logs. On top of that, train model orchestrates the full multi-epoch routine. We create an AtomW optimizer, but only over parameters that are marked requires grad equals true, which is perfect for the feature extraction phase where the backbone is frozen. We use NN cross-entropy loss since the model outputs raw logits for 3 classes. Each epoch we call run epoch once for training and once for validation, stash the results into a history dict, and print a compact status line. We also keep track of the best validation accuracy and clone the model's state dict when we hit a new best, so at the end we can restore the strongest checkpoint automatically, no accidental overfitting to the final epoch. Finally, plot curves draws side-by-side charts for loss and accuracy over time, train and val, so you can spot healthy learning, both lines, improving, plateaus, consider a smaller LR or more epochs, or overfitting, train improves while val stalls or degrades. This set of helpers gives you a tidy, production-style training loop with checkpointing, clear prints, progress bars, and quick diagnostics. Now we'll run Phase 1, Feature Extraction, where the backbone is frozen and only the new classifier head learns. This is the quickest way to get a strong baseline because we're reusing the pre-trained visual features and just teaching the final layer how to separate pizza, steak, and sushi. We set a modest learning rate, 1E-3, 0.001, which is usually plenty when you're training a small head on top of a fixed feature extractor, and we train for 15 epochs to let the classifier settle without overfitting. Calling train model kicks off the loop with our train and test loaders. Under the hood, it uses AtomW on the parameters that still require gradients, just the head right now, tracks loss and accuracy each epoch, and keeps the best checkpoint by validation accuracy. After training, plot curves shows two charts, loss train versus val and accuracy train versus val. A healthy run here looks like steadily falling losses and rising accuracies that flatten out as learning converges. If validation lags or bounces, try a slightly lower LR or a few extra epochs. If training leaps ahead of validation, consider light regularization, more dropout on the head, or stronger augmentation. Once you're happy with this baseline, we'll unfreeze the top blocks and fine-tune with a smaller learning rate to squeeze out a bit more accuracy. Now we move into Phase 2, fine-tuning, where we let the pre-trained backbone learn a little from our specific data. Instead of unfreezing the entire network, which can overfit or destabilize training on small datasets, we take a gentle approach and unfreeze only the last two EfficientNet feature blocks. These top layers encode higher-level patterns, textures, shapes that are most relevant to adapting from ImageNet to our food images. Because the backbone already contains good features, we use differential learning rates, a smaller LR for the backbone so it nudges weights carefully, and a larger LR for the head so the classifier can still move quickly. We keep cross-entropy loss and build an AtomW optimizer with two parameter groups to apply those distinct LRs. The train fine-tune loop reuses our run epoch routine under the hood. It trains for a few epochs, evaluates each round on the validation set, and tracks the best checkpoint by validation accuracy, restoring it at the end. This protects you from finishing on a slightly worse epoch due to random variation. After fine-tuning, we optionally merge the Phase 1 and Phase 2 histories, so plot curves shows a single continuous view of training. You'll often see a nice bump in val accuracy and a small drop in val loss as the unfreezed blocks adapt to pizza, steak, and sushi. If you notice overfitting, train improves while val stalls, reduce how much you unfreeze, try only the last block, lower the backbone LR further, or add a bit more augmentation. Time to see how well the model actually performs on unseen data. We switch to evaluation mode with model.eval, so layers like dropout and batch norm behave consistently, and we wrap the loop in torch.inference mode, open parenthesis to disable gradients. This makes inference faster and lighter on memory. For each test batch, we move images to the correct device, run a forward pass to get logits, and convert them to class probabilities with softmax. We then take the argmax to get predicted class IDs and collect three things for later analysis: the probabilities, all probs, the predicted labels, all preds, and the true labels, all targets. After processing the entire test loader, we concatenate the lists into full tensors and compute a simple headline metric, test accuracy, by comparing predictions to targets and averaging the matches. This gives you a clean, trustworthy score on data the model never saw during training or fine-tuning, and it sets the stage for deeper diagnostics like a confusion matrix and misclassification review in the next step. Let's dig into where the model gets things right and wrong. We start by installing and importing scikit-learn's metrics, then build a confusion matrix from the full set of test targets and predictions. The matrix shows true classes along one axis and predicted classes along the other. Big numbers on the diagonal mean correct predictions, while off-diagonal counts reveal confusions. For example, steak predicted as pizza. We render it with confusion matrix display, add class labels for readability, and use a simple blue color map. This gives you an immediate visual of which pairs of classes are most often mixed up and whether one class is systematically harder than the others. Below the plot, the classification report breaks performance down per class. Precision of what we predicted as this class, how much was correct. Recall of all items in this class, how many we found. And F1, their harmonic mean, plus support, class sample count. This is especially useful if the dataset is imbalanced or if you care more about certain mistakes than others. If you need a normalized matrix, percentages instead of raw counts, you can call confusion matrix normalize equals true to turn each row into rates. Use these diagnostics to guide your next tweaks. Improve augmentation for the most confused class, adjust fine-tuning depth or learning rates, or gather a few more examples for the weakest category. Let's go beyond overall accuracy and inspect the mistakes the model is most confident about. These are the dangerous errors. We first identify all misclassified test examples by comparing predictions to targets, and if there are none, we celebrate and exit. Otherwise, because the test loader doesn't shuffle, batch order matches the dataset order, so we can index directly into test data. From the full probability matrix, all probs, we extract each example's predicted probability for the class it chose. This is our notion of confidence. We then filter to the wrong examples, sort them descending by confidence, and display the top 6 in a grid. For each image we show the photo, inverse transformed to a viewable format, the predicted label, the true label, and the model's confidence. This view is invaluable for debugging. Are high confidence mistakes tied to specific lighting, angles, or textures? For example, steak char that looks like pizza toppings, or sushi rolls that resemble steak slices. Use these insights to guide data augmentation, crop, flip, color jitter, collect a few targeted samples for the confused class, or tweak fine-tuning depth and learning rates to better adapt the backbone. Let's finish with inference on your own image. This cell downloads a picture from a URL, runs it through the same auto-transforms the pre-trained backbone expects, and feeds it to the model to get a prediction with probabilities. The helper predict image switches the model to eval mode and wraps inference in torch inference mode so it's fast and memory light. We convert the PIL image into a tensor via the auto-transforms, add a batch dimension with unsqueeze 0, move it to the right device, and run a forward pass to get logits. Applying softmax turns logits into class probabilities. We take the argmax to find the predicted class index and return both the index and the full probability vector. In the main block, you can paste any pizza, steak, sushi image URL. We fetch it with requests, open it with PL, call predict image, and render the photo with a title showing the predicted label and its confidence. If the download fails, bad URL timeout, you'll see a friendly error message. Pro tip: if you want to test local files or Colab uploads instead of URLs, just replace the download step with image.openpath/your_image.jpg. Convert to RGB and reuse the same predict_image function. Here are some great ways to level up this project framed as a practical roadmap. First, train longer in both phases. Extend the epochs and watch how the curves evolve. A gentle LR drop in phase 2 often turns small gains into stable improvements. Next, Swap the backbone, try ResNet 18, ConvNeXt Tiny, or VIT B16. Update the weights, enum, and final head dimension to match, and compare speed, accuracy trade-offs. For augmentation, move beyond weights, transforms, and craft a manual pipeline with random resized crop, color jitter, and random horizontal flip, but keep ImageNet normalization. This often boosts robustness on small datasets. Deepen your confusion insights by reporting per-class accuracy, listing the most confused class pairs, and showing a few example images for each class. This explains why the model makes certain mistakes. Explore progressive unfreezing. Start with just the classifier, then unfreeze the last block, then the last two, and so on. Track validation accuracy to find the sweet spot between adaptation and overfitting. While fine-tuning, experiment with differential learning rates. If the backbone LR is too high, you'll see validation wobble or regress. Dial it down to keep updates gentle. Make the workflow portable by saving the best state dict and writing a small reload function for inference in a separate script or service. Finally, test generalization with out-of-distribution images, say a salad, and discuss how the model behaves when the input isn't pizza, steak, sushi. This is a great segue into confidence calibration, thresholds, and OOD detection in real apps. Here are the big takeaways to lock in. Always use the transforms bundled with your pre-trained weights, so your inputs match the backbone's original training distribution. This avoids silent accuracy loss from size or normalization mismatches. Kick off with feature extraction, freeze the backbone for a fast, strong baseline, then fine-tune selectively, unfreeze the top blocks, and use smaller learning rates to squeeze out extra performance without overfitting, and rely on visual diagnostics to guide your next moves. Learning curves reveal optimization issues. The confusion matrix shows which classes get mixed up, and a most wrong gallery spotlights high confidence mistakes you should target with augmentation, data fixes, or tuning.